Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. Alright, so in this video I will talk about the Biot-Savart law. So basically this law will be used in order to derive expression for the magnetic field intensity or the vector of H, and the unit for the magnetic field intensity is equal to ampere per meter. Alright, so as we have been learned in electrostatic, so one of the most important step that we need to do, okay, in order to analyze a field in an electric field is to find the expression that represent our electric field intensity. Alright, so let's consider a simple case like this one. So we will have the charge. So the charge is the source for the electric field. So depending on the sign for this charge, so let's say we are considering a positive sign for the charge, so we will have the electric field that produced by this particular charge is in direction upward from it. So how can we find the expression of electric field intensity at any test point? So let's say in this particular case at this point, and we call it this point as a P point. So what we'll have to do, so first we need to derive the vector of R, which is represent the direction and distance between the source for the electric field and our test point here. So we have the vector of R, and then so by using any law, related law, for example we are using a Coulomb's law, so we can derive the basic expression that represent our electric field intensity as given in this equation. So we have a vector of E is equal to R cap. So R cap is the unit vector for this vector. So 1 divided by 4 pi epsilon multiplied by Q divided by R squared. So whereas this is the distance between the charge and the test point. Alright, so similar like what we have in a magnetic field, okay, especially particularly in a magnetostatic, the source for the magnetic field is come from a current. Alright, so let's say in this case, so we have a current, okay, that flowing inside the conductor in this direction, and by using the Grab's right hand law, alright, so we have this, the thumb will be referring to the direction for the current, and our fourth finger will be represent the direction for the magnetic field induced. So in this case, so the current will be flowing in this direction, so we will have the direction for the field induced in this direction. So therefore in this side of the conductor, so we will have the direction of the field is out from our pitch here, so flowing outside here. Alright, and this particular side, so we will have the direction for the field induced is flowing inside our paper. So let's say we want to find, or we want to express the expression for the for the magnetic field intensity in this P point, for example. Alright, so by refer to the Biot-Savart law, so the expression for the H can be expressed like this one. So we have dH equal to I divided by 4 pi. So this is the vector of the L. Alright, so the distance that represent the current flowing here, so cross with R cap, so this is the unit vector that represent our vector here, so divided by R squared. Okay, so similar that like what we have in electrostatic, so this is the distance between the current and the test point here. So this equation can be solving by integrating both parts. So we will have the vector of H here is equal to I, so divided by 4 pi, line integration of vector of the L cross with the R cap, or the unit vector for this vector, so divided by R squared, and the unit for the H is equal to ampere per meter. Alright, if we compare to the both field characteristics, so we will see that basically both field intensity are in distance dependence. Okay, so whereas the far our test point from the source of the field, so basically the lower value of the field intensity will be produced, and the factor of reduction is in terms of R squared. And if we compare both field as well, so we will see that so the direction for the electric field intensity is the same direction as the distance of the vector distance of it. Okay, so however, in a magnetic field, so the direction for the field is orthogonal with the this vector of r. Okay, so let's say in this case, so the direction of the r is given in this direction. So however, so basically the field direction will be either flowing outside or flowing inside to the our plane. Okay, so depending on the direction of the current, as I mentioned just now. Alright, so in order to understand, so how can we apply the Biot-Savart law in order to express our magnetic field intensity? So let's look at this example. Alright, so we have one conductor, okay, with the length of L, and then inside that particular conductor, so we have one current that flowing inside that particular conductor, and the direction of the current flowing will be in a z direction. So we need to find the expression for the field magnetic field intensity at this point. Okay, so because of the direction of the current in this case is flowing in a z direction, so we will have our field intensity here will be flowing inside our page. Okay, so by referring to the right hand rule as I mentioned just now. So we have three vector here. So first, in the middle of this conductor, so we have the vector of r. So we have another vector by referring the direction, the distance between our upper limit for the conductor with the test point and the lower limit of the conductor with the test point. Alright, so we have radius here. Okay, so the value of r that represent the radius between the center of this conductor and our test point, and basically we are make this r with the angle of 90 degree, okay, compared to the r and our z-axis here. So we have three different angle, so which is theta 1, theta and theta 2. So this is the average of the angle between these two limits. Alright, to represent the angle between our current here and our test point here. Alright, so by referring to the general expression for the magnetic field intensity from the Biot-Savart law, so we have dH is equal to I multiplied by the dl vector cross with r cap divided by 4 pi r squared. Alright, so similar what we have in Coulomb's law previously. So the unit vector is equal to the vector divided by its amplitude. Alright, so if we refer to this vector of r, so the r cap is equal to this vector, so divided by its amplitude. And if we put this expression inside this expression, so we will have the r cap divided by r squared. Okay, so in this side of the equation, so will be equal to vector of r, so divided by its amplitude, so dot with 1 over r squared. Then we will have the expression for this is equal to vector of r divided by r with the power of 3. So by considering this representation, if we put back inside this equation, so we will have another equation that represent our magnetic field intensity, or dH. So whereas dH is equal to I dot with the vector of dl cross with a vector of r, so divided by 4 pi r the power of 3. Alright, so by referring into this figure, so we will find out, so our vector of dl here is represent the direction and the length of the conductor where the current flowing. So in this case, so the current is flow in a z direction here, and the variation of the length is given by the dz. So that's why our vector here will be represented by z cap dot dz. So the vector of r in this case is equal to this vector. Alright, so this vector is travel from So let's say this is the coordinate of this is represented by 0, phi and z. Okay, so the vector will be travel from 0, phi and z to this point, whereas this point is represented by this coordinate, so r, phi and 0. Alright, and based on this condition, so we will have the expression for our vector of r is given by this expression r cap r, so divided by z cap z. So if we solve this operation, so we have the vector of dl is equal to z cap z cross with the vector of r, so this expression. So the result of this operation, so we will have, so z cap cross with r cap, we will have direction in theta cap. Alright, so whereas in this operation, so z cap cross with z cap, we will have 0. So that's why we only consider this first two of operation. So we will have the result for this operation is equal to phi cap r multiplied by dz. Alright, so once we solve that part of the equation, so we can rewrite our equation to become like this. Alright, so we will have the vector for dh is equal to phi cap. Alright, so based on whatever we solve in this part, so phi cap I r dz divided by 4 pi. So the expression for the distance here, okay, so we are based on this vector, so we will find, so the amplitude for this vector is equal to r squared plus z squared and square root of it. So we will have r squared plus z squared with the power of 3 divided by 2. So in order to solve this equation, so basically we need to make some modification. The first modification, so we need to convert the z component to the theta. Alright, so because in this case, so as we can see here, one of the parameter that change is the theta. The theta will be changed from theta 1 until theta 2. So that's why we need to express our z component in a theta, in a term of theta. Alright, so first, so based on this triangle, okay, so if we look into this triangle, so basically the tangent theta can be represented by r divided by z. Okay, so the length of this from our origin here to the center point of the conductor. So if we rearrange this equation, then we will have z is equal to r divided by tangent theta, or we can express this expression is equal to r cotangent theta. So from this expression, if we perform derivative operation, so dz divided by d theta, so we will have dz is equal to minus r cosecant the power of 2 theta d theta. Alright, so based on the expression that we derived just now, okay, in order to express our z component in the theta term, so basically we can replace whatever expression that we have into our original expression. So we will have, this is the expression that result from this step. We follow from one step to another, right? And with application of the knowledge for the trigonometry, so we will find the dh expression can be expressed in this case is equal to this expression. So we have dh is equal to phi cap, so minus I divided by 4 pi r, integration from theta 1 until theta 2 sin theta d theta. And the solution for this expression is given by this expression. So whereas, so in this case, so we have our vector of h here, okay, is equal to phi cap 1 divided by 4 pi r cos theta 2 minus cos theta 1, and the unit of it is equal to ampere per meter. Alright, so based on the equation that we have been derived just now, so this is our expression for the vector of h. So if the conductor is semi-infinite, with respect to the P. Okay, so in this case, so the length of the conductor will be start from origin to the infinity value. So we will have theta 1 is equal to 90 degree, and theta 2 will be equal to 0 degree. Alright, so in this case, so if we have this line, this line is start from origin into infinity, so we will have the theta 1 is equal to 90 degree, and the theta 2 will be almost equal to 0. Okay, because we are considering a very high in terms of a slope line of this triangle. So in this case, if we replace the theta value inside this expression, then we will have the expression for the vector of h is equal to theta cap, so I divided by 4 pi r with a unit of ampere per meter. So however, if the conductor is infinite with respect to the P, so that means that we have a very long the length of the conductor, okay, from minus infinity to the infinity. So we will have, so our angle of theta 1 here will be almost equal to 100 degree, and the value for the theta 2 here is almost 0, with the same reason as previous case. So in this case, if we replace the value for the theta 1 and theta 2 inside this equation, so we will have the vector of h is equal to theta cap I divided by 2 pi r. Okay, so as given in this example, so we will have our unit vector is equal to phi cap. Okay, because normally if we have line current like in this case, so we will have a cylindrical shape of magnetic field, and because of that, the unit vector that represent our expression for magnetic field intensity is in a phi cap direction. So however, in the some cases, so the unit vector need to be changed. So in order to derive the unit vector here, alright, so we have one general expression like this. So we have unit vector for the vector h is equal to L cap cross with the R cap. So whereas L cap will be the unit vector along the line current. Okay, so for example in this case, so definitely in a Z cap component, so that's why we are using the L is in a Z cap component, and the R cap will be the unit vector along the perpendicular line from current to the point. So for example in this case, so the R cap will be in a component of R. Okay, so in this case, but some of the case, so the line and the field will be expressed in the XY Cartesian coordinate system, for example. So in that particular case, so you need really sure, so what is the unit vector for the current flowing direction, and what is the unit vector that represent the vector between our line current here and our test point. Alright, so in order to express your understanding, so let's say in this case, so we have instead of whatever we have here, so in this case the center of the conductor is placed in the origin, okay, of the ZR coordinate system. Alright, so in this particular case, so we will have our general expression for the magnetic field is given as this expression. Okay, so similar expression that what we have been derived just now. Alright, so based on this case, so you need to find what is the other expression of the H can be considered, okay, or can be derived by considering the parameter given in this figure. Alright, so as a tips, so you need to express the cos theta 2 and cos theta 1 by using L and R, or any other parameter that you may find in this figure. And then, so based on this expression, so you need just put back inside this expression to get another expression, which is that particular expression directly represent so whatever physical setting that we have here. Okay, So you need to use your own handwriting, so put your name and matrix number in the answer. Alright, so scan and submit through the link that provided. Alright, so that's all for now. So should you have any problem, so please do not hesitate to send to me. Alright, thank you and good luck.